Okay, let's get started. This is not your demo. This is the demo that works, but that has the flywheel is too small. We're still working on the other one. Maybe Thursday. We'll get there. Where are we? Yeah, you heard that. We're here, have a regular lecture today. We will talk about constraint classification and non-holonomic constraints. We're a little bit behind with respect to this schedule, but that doesn't really worry me because we have buffer built in. I want to remind you that on Thursday we have another exercise, so don't forget your laptop, your MATLAB installation, work on the homework. What we will do, I already mentioned this on last week, we will basically work on two routines. One is called compute natural dynamics, and the other is called integration step. Compute natural dynamics computes accelerations if there are no external forces and torques present. And integration step integrates those. And integration step is part of the homework. Did anyone try this already? Did you see spirals or circles?
The axis, the velocity was a spiral, and the first one was some. It was like the first one was correct, the second one was not. It was spiral.
Okay, and what did you do to fix the spiral?
I'm still working on that.
Okay, that's my experience with this exercise. Seems simple. Seems simple on paper, but the question that you and then everyone else should ask themselves is, what am I integrating? I'm integrating coordinates. So numerically integrating numerical derivatives, but what we get are accelerations and velocities, which are physical derivatives. And those two are not the same. That's the important bit. And if you wrongfully assume that those two are the same, you will see spirals. Yeah? So I'm glad that you confirmed that expectation, but everyone else will see this. And so basically integration step is part of the homework, and then we will do the compute natural dynamics in class. In a sense, get this animation going, right? I showed you this when we talked about the equations of motion of a rigid body, and now the goal is that you get this to work yourself. With in going back to the lecture, sorry, any questions? Going too fast. No. Going back to the lecture, we talked about now constraints. This is where we go from individual bodies to systems of rigid bodies that are somehow connected with constraints. And we talked about joints as something that enables motion and that restricts motion. Where your knee joint allows your knee to bend, compared you wearing a cast, but it also prevents your lower part of the leg falling off from the upper part. And in the human body, this is physically done through ligaments, right? And these ligaments can rupture when you injure yourself. And then, of course, the leg will not fall off because it's still held together by skin and muscle and other things. But sort of functionally, when this ACL, this anterior crucial ligament, when this rips through or breaks, then the two are not connected anymore. And that will feel weird, and then require a cast, which means your leg cannot move anymore, which then basically means you have the other function of the joint. You don't have the other function of the joint. So philosophically, two different ideas. Joints enable motion, they restrict motion. We will take both viewpoints through two different formulations, either explicit constraints or implicit constraints, where here I have motion primitives that are described through generalized coordinates q, and those generalized coordinates explicitly create some motion in x, where x is something that we haven't defined well, but always somehow corresponds to orientations and positions of bodies. And we have implicit constraints, where I basically look at this x, which is the unconstrained motion of these bodies, and I reduce it through additional equations to fewer degrees of freedom by saying that some g of this x has to be equal to 0. We went through this and extended it to velocities, where we found a nice linear relationship through what we called the Jacobian. And of course, we got two Jacobians. For the explicit constraints, we got an explicit constraint Jacobian, JF, which if you multiply it with the generalized velocities, q dot, you get the velocities in which your system moves. And this JF hence describes the directions of motion in which a body can move. The columns of JF are the directions in which your x, in whatever weird space it is defined, but in which your x can move. For implicit constraints, we got a different Jacobian, JG, that if multiplied with your vector of Cartesian velocities, your x dot, should give you a 0. And I told you to read this as a bunch of dot products, where basically every column of this Jacobian is multiplied in the sense of a dot product with a vector x, and that dot product has to be equal to 0, which kind of means you cannot move in this direction, right? Your direction has to be orthogonal. The direction in which you move, your x dot, has to be orthogonal to the direction which is given here. So JG has the exact opposite meaning. The columns of JG are the directions in which we cannot move. And those directions are orthogonal to each other, right? The directions in which I move and the directions in which I cannot move are orthogonal, and I can represent this by taking the matrix product JG transpose times JF. Means every column of this is multiplied with every column of JF in the sense of a dot product, and all of them are 0, so they're all orthogonal to each other. I want to extend this to accelerations, and if you're not using the template, leave a little bit of space. But I want to now talk about accelerations. And we're going to do the same thing, simply take derivatives, and I start with explicit constraints, where my x double dots, so the acceleration in this x space, is given by, now we simply apply the product rule, so I get JF times Q double dot plus JF dot times Q. We get two terms, and this is quite typical for constraint systems, where I get an acceleration because I have a Q double dot. So my motion primitive, my generalized acceleration, my generalized velocity changes, giving me a generalized acceleration. And that, of course, leads to the fact that I get an x double dot. So this is the acceleration from change in generalized velocities. So my q dot change, I get generalized acceleration, and that gives me, of course, an acceleration in my x space. Where does this come from? What does this describe? J dot times q dot. What is J dot? It's kind of weird. time derivative of a matrix. But if you think about what JF means, right, the directions in which you move, and if I put a dot over that, it means basically the directions in which you can move change. So we have here a change in the constraints, and we get an acceleration from changing constraints. And I can make a quick drawing going back to our original example, right, where we had basically this idea of a door described by the position here in the middle. And depending on how fast we move here in our q variable, we will get an acceleration of this point this way. Sorry, a velocity of that point this way. So this is to some time t0. And then I wait a bit. And as I wait, of course, my door will move. That point now is here. And I get a change in velocity, right? I get a new velocity that I drew a little bit longer. So this would be x dot as a vector at some time t1, and this would be x dot at some time t0. And here we can sort of nicely observe the two effects, because they're clearly separated. Number one, I changed my q dot. So I went from a q dot that gave me this acceleration at time t0 to a larger q dot that gives me a longer arrow here. So I had some acceleration q double dot. That changes the length of these arrows. But they also point to a different direction, right? The directions in which I can move in this situation, right? I always have to move around the circle. And if I'm in this situation, it means going that way. If I wait a little bit and this body has moved, that direction points in a different direction. So my angular velocity changed its direction between t0 and t1, and that means there has to be some acceleration. That's the second part here. How about implicit constraints? Well, sort of same thing. If I take another time derivative of my 0, I will still get a 0. And then I will get jg transposed times x double dot plus jg transpose dot times x dot. Similar idea, right? Here I have a change in constraints. And what this is basically telling me is that because the sum of these two has to be 0, a change in the constraints leads to some implicit acceleration that has to be compensated through some x double dot. We will call these bias accelerations later. But I get a bias acceleration here and has to be compensated through the actual acceleration in x, because the sum of these two has to be equal to 0. We can do this for the little roller coaster example that we started in the last lecture. So I have x double dot, if I go through explicit constraints, that is going to be jf times q double dot plus jf dot times q dot. So let's see what we have. This was jf, 1 over 2q. Times q double dot plus, and now I need jf dot. So that's 0 and 2q dot. Right? The time derivative of 1 and 2q is 0 and 2q dot, which get multiplied with q dot. And it's very typical of these bias accelerations that we have these square terms, squared velocities, where in a sense you can think about the velocity on one end changing the constraint, and then the velocity creating a motion along that constraint. And the product of these two gives me an acceleration, because a motion of a constraint and a changing constraint together give me an acceleration. Means here, right, if I move along this path with a constant q dot, so with a constant velocity in x direction, q double dot is going to be 0. I will not see an acceleration in x, because I'm moving with constant velocity here, but I will see an acceleration vertically. Right? Because as I move with constant acceleration this way, the direction in which I move, these orange arrows, they change, they tilt more and more upwards, and that requires an acceleration in the y direction. For the implicit constraints, we have 0 being equal to j g transpose times x double dot, plus jg transpose dot times x dot. So I get 2x and minus 1 times x double dot y double dot. And sorry, this shouldn't have this. No, it doesn't matter. It's a one-dimensional constraint, so I can remove all these arrows, but they're not really wrong in that sense. What's the time derivative of jg? Who can help me with this quickly? This is jg. What is it? Its time derivative? Two x dot, right? Time derivative of 2x is 2x dot, and of minus 1 is 0, and that now gets multiplied with our velocities now in x space, x dot and y dot. And in a sense, the same idea, right? I cannot simply say I don't have an acceleration, x double dot and y double dot equal to 0, because then this first term would be 0, and the last term would evaluate to 2x dot square. Right? And then if I get 2x dot square, as soon as I have some velocity in this direction, I need some acceleration here in this first term so that the sum of these two is equal to 0. Same idea, right? This somehow changes the directions in which I cannot move. And to make sure I compensate for this, I need some accelerations. So I have to adapt the directions in which I move through some accelerations, in this case x double dot, y double dot. So, any questions about implicit and explicit constraints? I have a question for you. Let's go back to this example, and maybe I'll do this here on the board. We said we want to do an implicit constraint for this guy. And that guy is basically defined because I have a point B here. And what were the coordinates of this point B? Simply x and y. OK? And those, they had x naught and y naught, but I'm just going to give them 0 and 0. Doesn't really change the problem. And then we set up here these implicit constraint equations that looked like this, where we basically went through this point has to be the same on the door and on the door frame, which is what we write here. And so we got these constraint equations. Now, what I want to do here is a different constraint equation, where I realize, hold on, if that point rotates around about this point, I get a distance d. Yep. And that distance, of course, has to be constant. And I could compute that distance d by simply saying d equals d squared equals x squared plus y squared. And then let's throw this all on one side of an equation and say this equal to 0. OK? You follow, right? This says that distance is that square plus that square. And if those are equal, then the difference between them has to be equal to 0. And that gives me a neat little implicit constraint. What are your thoughts? You have a thought?
Do we need the parentheses?
Here? No, we don't. It's a sum. But they don't hurt. What are your thoughts? Right? That seems to make a lot of sense, right? That point B has to keep that distance, so I turn this into my constraint. It seems like your instructor is not happy with what he wrote down. Why? So what's the first thing, if you compare this with the constraint that we had over here? What's sort of the first thing that comes to mind? Can those two really describe the same thing? You should get this, right? Can this constraint and that constraint be the same? The voice of the instructor suggests that the answer is a very clear no. Why not? Why not? How many constraints do we have over there? 2. How many constraints did I have right here?
1.
OK, so I'm missing something. Yes. If I do this, if I keep that distance the same, I still could go ahead and say, well, this whole door rotates like that, which wouldn't be good, right? That rotation of this door like this would keep the distance the same, but would not fulfill sort of the original constraint that we had in mind. So I would have to somehow, and this is another indicator, we never talked about this angle gamma that describes the orientation, which is very prominent in these equations. So I would have to do something here where I define a gamma over some tangent x over y. Or the other way around, yeah, tangent gamma is x over y or something. So this is an important point. If you think about these constraints, make sure you have the expected number of constraints. If I have a body that has 3 degrees of freedom, and I eventually want it to move in one motion primitive, I need 2 constraints. And if I can just come up with 1 constraint, I must have made a mistake somewhere. So just a check. Right? These things seem simple at first, but can be quite tricky. What else did I want to show you? I want to discuss with you this Jacobian. And we have, in a sense, a definition mathematically where we said this jf is the partial derivative of our constraint function against the generalized coordinates. And if you know partial derivatives, it basically means I have, this is a vector valued function, so I have an fc1, fc2, fc3. So in each row, I have a component of fc, and then in each column, I have a component of q. And this gives me this nx by nq matrix, where I have here nx components, and in this direction, nq components. And what it does is gives me sort of vector valued our Cartesian velocities from the generalized velocities. And I can now go ahead and read this row by row, because the first row will give me the first component of my x velocity. Second row would give me the second component of my x velocity. And in general, right, xi dot depends only on fci, fci, fci. And then I take the partial derivative against q1, q2, and so on, and multiply with this vector q dot. And I end up, if I evaluate this matrix product, in the first row, I get jfci partial q1 times q1 dot plus partial fci partial q2 times q2 dot, and so on and so forth. So the velocity in a particular direction is the sum of all the individual generalized velocities multiplied with some factor, right? And those factors are the entries of my Jacobian. Here's a little example where I have a robot that has a q1 here, a q2 here with the associated generalized velocities. And my vector x, in this case, is not describing everything, but I'm just interested in the position of the end effector, x dot and y, x and y, and then the associated velocities are x dot and y dot. And those x dot and y dot, they follow from jf times q dot. And jf, in this case, has to be a 2 by 2 matrix. So far, I hope everyone's on board. Now, can I try to geometrically understand what these components, right, these entries in my Jacobian mean? And I can do this by thought experiment. And what I will do is I simply imagine that q1 dot is equal to 0. So this joint is blocked, and q2 dot has unit velocity. So q2 dot is 1. Then the velocity that we get here is simply going to be b over d in a vector. That's what the math gives us, right? And in more general case, we get b over d times q dot, q2 dot, right? This is what the math gives us. What does the physical intuition give us? Well, we have somehow a translation from a rotational motion over this guy into a linear motion of this thing. And that requires a lever arm. Right? When I have a rotational motion and I look at a linear motion, there's some lever arm between these two. Now, if I'm just interested in the x component, x dot, right? And I can basically decompose the overall velocity here as a component in x direction and a component in y direction. What is the lever arm that will give me this x velocity relative to the angular rate that I have here? Where's that lever arm? And to this, it actually only matters in which direction we're moving. And we have to look at exactly this distance here. The larger I make that distance, the larger x dot is going to be for the same q2 dot. I hope everyone sees this, right? If I move further down, I will have a longer lever arm. I will get a larger velocity this way. More precisely, that velocity, x dot, the component in this direction, is equal to that distance times q2 dot. In other words, what is this distance? q2 dot times this is giving me x dot. So that distance here is exactly b. Very, very simple lever arm. Where does the distance d show up? Now I'm thinking about a motion in this direction. Where does that distance d show up?
Maybe from the joint Q1 dot perpendicular to the line we draw.
So we're still talking about q2 dot because I'm interested in this d here. So that gets multiplied with q2 dot and gives me
The distance from the top of T to the tool center point.
from the tool center point to where?
To the joint Q2 on the horizontal line.
Okay. Now I got you. You're talking about this, right? So this would be the distance d. The vertical distance from our point of interest to the corresponding joint. A?
Would that be a Q2?
No. So A now gets multiplied with Q1 dot. So to reason about what A does, we have to think about this basically setting Q2 dot to 0 and only allowing motion about Q1 dot. Right? So I now freeze that joint and allow motion about this joint. Now I need the lever arm between, well, this point and, again, my end effector. So this distance here is A. And to be precise, I write minus A because a positive Q2 dot will give us a positive motion of the end effector this way. A positive Q1 dot will give me a negative motion, right, in the negative x direction. And then lastly, I hope you see where this is going. I need this distance. That would be equal to c. So if I think about this just geometrically, this Jacobian, which is weirdly defined over these partial derivatives, and that we interpret it as directions in which we can move, all of a sudden becomes another meaning, that of lever arms. Right? These are simply lever arms that somehow translate a rotational motion into a linear motion. And if I have sort of this relationship between rotational motion, linear motion, we should also expect something with units of meters here. Right? Those are radians per second. Those are meters per second. So whatever I put in between must have units of meters. So these are simply distances. Sometimes,
Can you emphasize why is it negative data?
if I have a positive Q1, this point will actually move to the left. Yeah, and that's why I get a negative value here. So if I think about this as a positive distance, I need a minus sign.
Isn't it the same with B? Like the Q2 moves.
When Q2 has a positive direction, this guy goes to the right, because then I'm rotating about this point. Right? So you can decompose these Jacobians by looking at them one axis, one generalized coordinate at a time, freezing the others, setting them to 0, setting the velocities to 0, and you can interpret your Jacobians.
The arm extends when Q2 dot moves like
Yes, it does. This is Q2, right? So I get this motion, so positive x direction, positive y direction. If I move about joint Q1, sorry, this is, okay, this doesn't really work. If I move about this joint, you basically see this end effector going towards the left and up. Right? So this is where the signs come from. But don't worry about this, right? This is not how we're gonna get Jacobians. We always will compute the partial derivatives. But I want for you to understand these are lever arms, right? And then if we'll see this in one of the exercises, I sometimes have not only rotational joints, but also translational joints, right? If so, for example, if I have one Q that describes the motion of the blackboard up and down, that doesn't really work anymore, because the lever arm, there's no translation from linear to rotational motion, so there is no lever arm. Then you really just have a direction, which for this motion would simply point in the direction which we can move with unit length, right? Then this idea of lever arms doesn't really apply, or applies in a more directional sense, where the transmission ratio is going to be exactly 1. Questions? I then want to spend some time on constraint classification. And I showed this example in one of the exercises where we, exercise 1 to be precise, where we build a sim mechanics model of it, where we have 1, 2, 3 bodies connected with 1, 2, 3 rotational joints here. And then we had sort of this interesting time-dependent input. And we have here a unilateral constraint where we said that this point can move freely in space but cannot go through that wall. And I now want to classify the constraints that we see in this image. And let me number them. So this joint is 1, 2, and 3. This would be joint 4. And this would be somehow constraint 5. And we talked about explicit and implicit constraints as a bit of a choice. Are we interested more in how motion can be generated? Are we restricting motion? Are we creating motion? Now, if you look at those 5 constraints that I have here, what is more appropriate? Should we use explicit constraints or implicit constraints to model them? What would you do for joint 1? Explicit or implicit? Implicit. Why?
Because it's restricting motion.
But it's also enabling motion, right? So joint here, it's called joint 0, but what I labeled 1 here enables motion about this axis, right? That's kind of the difficulty. It does both. What aspect is more important at that point?
Depends on what I want to solve. Like maybe I use explicit if I want to know position of point.
I think I can generalize this a little bit more. Because if I look at this joint, I know it has a well-defined joint axis. I already assigned a variable to it, right? I have a Q0. If I look at these joint, right, we said that variable actually has a spring damper mechanism or a motor attached to it. So I'm somehow interested in what are the Qs. And I do have Qs. And whenever I have the situation, right, and in robotics, that's about 95% of the time, I have somehow a joint that has a motor and the sensor, and I have a generalized coordinate that I can measure and that I can influence, then I would go ahead and use explicit constraints. What about this guy here, right? This kinematic input. I could go ahead and describe this as an explicit constraint. But to do that, I would first have to introduce a bunch of additional Qs. A Q that describes how long the cylinder is, a Q that describes what angle it has in space, and so on and so forth. I could just say that distance here is equal to some value that depends on time. Very similar to what we wrote down here. And in this case, that would be the only constraint. Because all it does, this hydraulic cylinder, right, it rotates here, it rotates there. All it does, it constrains the length. So writing that as an implicit constraint would be much, much easier. A second reason is that this is part of a loop. And we will later see that when we do loop joints, it's much easier to work with implicit constraint. Because if I go ahead, right, I would assign a Q here, a Q for the length, a Q for the angle here. Right? I would have to introduce all these motion primitives and generalized coordinates. And then I realize, hold on, I cannot determine them individually, freely, because they somehow have to fulfill the fact that this is a loop. So something like this we always will do with implicit constraints. And then the same down here. As an explicit constraint, this is actually easy to write down because all I have to say is I somehow compute the distance here, and that distance should be positive. Right? So we will see this in a second, that this is an inequality constraint. But again, here I don't have any Qs, I don't have generalized coordinates. I'm almost only left with the choice of doing this with implicit constraints. So this is how we should think about these. Yeah? Whenever possible, when I have information about what's going on in a joint, use an explicit constraint. Explicit equations are simply easier to work with. If I don't have that because I have a loop joint or contact or some other special situation, that's when we normally then revert to implicit constraints. Next constraint classification are equality constraints and inequality constraints. Equality constraints is everything that we've seen so far, where say x equals fc of q, or g of c, gc of some x is equal to 0. An inequality constraint can actually only be an implicit constraint, where I basically replace this gc of x is equal to 0 by an inequality where, say, gc of x is larger or equal to 0. In our example, the first 4 joints are all equality constraints. This would be an inequality constraint. And it's basically what I said before. If I find a mathematical expression for this distance, I will simply say that distance, which is jc of x, right, that somehow depends on the position and orientation of this body. From the position and orientation of this body, I can compute that distance, right, a yc in this coordinate. And then I simply say that distance has to be positive. If it's positive, that point is away from the wall, and I'm good. If it were negative, that point would be in the wall, and that's not what I want. Right? This would be an inequality constraint. Next classification are scleronomic and rheonomic constraints. Scleronomic means I have a constraint that is not explicitly time dependent. And everything that we looked at so far was scleronomic. Time does not show up as an explicit variable. Implicitly, yes, because q and x are variables or functions of times. So this x of t somehow depends on the q of t. But if q doesn't change, x will not change. This is different for rheonomic constraints, which do have an explicit time dependency, where my value x depends not only on the state of the generalized coordinates, but also on time explicitly. The same for implicit constraints, where I would say gc of x and time, t, has to be equal to 0. In our little example, the first 3 joint and constraint number 5 are scleronomic. Constraint number 4 is rheonomic. We said we will likely do this as an implicit constraint, where we say the distance from here to here, right? If I set this to 0, 0, then the distance would be x squared, x2 squared plus y2 squared. Right? So that distance depends on the x. Somehow is time dependent. Right? There's this idea that I have here a kinematic input. I have a hydraulic cylinder that doesn't create a force, but really creates a displacement, and that displacement is time dependent, changes over time. So that distance depends on, as a function of time. So if I would write this as a constraint equation, I would get something like x squared plus y squared. That's the distance, minus some distance that depends on t is equal to 0. And now you see here the explicit time dependency, which we didn't have before. Right here, x of y are functions of time, so this can move, but time doesn't explicitly show up. And that has interesting consequences. If I think about velocities, and I just think about, where are we? Just think about this equation, there's a trivial solution in terms of velocities. Right? This is a scleronomic constraint. What's the trivial solution that I can always do? Yeah, don't move. If the system doesn't move, you're not doing anything wrong in a scleronomic system. You will not violate constraints. This does not work here anymore, right? Because if I have an explicit time dependency, this will change, and that means that these variables have to change. Right? So I cannot simply say the time derivatives of these two to 0 and expect this constraint equation to hold forever, but they somehow have to react to what's going on here. And I mean, we clearly see this in this example here, that if this hydraulic cylinder is imposing a motion, the rest of the system, in particular body 2, has to move as well. So it has to have some x dot. What does that mean in terms of power? Right? And we have the difference here, right? These are all passive joints, ball bearings, basically. Here I have to say there's a hydraulic cylinder, right? And that hydraulic cylinder changes length. And it may change length against a force that is being transmitted here. So this is actually generating power, right? So rheonomic constraints can generate power, while scleronomic constraints cannot. In terms of velocities, right, for rheonomic constraints, we get an additional term. X dot is now jf times q dot. But now I also have to take into account the partial derivative of my constraint function against time. And for implicit constraints would be kind of the same. So we get jg transpose times x dot plus the partial derivative of jc against time. That has to be equal to 0. So here we basically see mathematically what I just discussed, that if this is non-zero, if that implicit constraint changes over time, the trivial solution x dot equals 0 does not fulfill my constraint equations anymore. Any questions about scleronomic and rheonomic constraints? Yes?
You also formulate a constraint with the power, so that you say, I don't want the power to exceed that value?
You could, but that would require a bit of a different framework.
Okay, so it doesn't make sense in that kind of
No. No. So if you really want a constraint that does not deliver power, it has to be a scleronomic constraint. And the reason why scleronomic constraints don't deliver power, we will see this a little bit later in more detail, but we basically have this idea, directions in which I can move and directions in which I cannot move. In a scleronomic constraints, the directions in which I can move, I don't have any forces, right? There's no resistance. This is where I can move. That's the whole idea, right? And those are the directions in which I cannot move. And the reason why I don't move in this direction is because there are forces. In the bearing, there's forces that keep the bearing in place. If I pull on that door, there's going to be a force in the hinge that prevents the door from being pulled out of the wall. But that force will happen in the space of JC, right? Those are the directions in which I cannot move. So this is where the forces live. This is where I move. And because those two are orthogonal to each other, the directions in which I move and the directions in which I experience forces are always orthogonal to each other. And power, being the dot product between these two, is always going to be 0. Right? So that's why in a scleronomic constraint, you never get power. With the rheonomic constraints, that changes a bit because I basically get two motions, right? I get the free motion in Q space. That's along the directions that we had before, given by JF. But now I also get a motion through the change in t. And that motion can go any other way. And then that motion is not orthogonal necessarily to the constraint forces. Right? As soon as I have a rheonomic constraint, it can deliver power. Because I basically, you see it here, right? I have basically this direction, that's my Jacobian, directions in which I can move freely. And then I get some contribution that is not in this direction. And that thing is not necessarily orthogonal to this thing. And if these two are not orthogonal, this is where the forces live. This is where, I haven't talked about forces yet, but this is where the forces live. This is where you move. And if these are not orthogonal to each other, you get power. Okay, good question. Any other questions? How do you keep these apart? How do you forever, and I literally mean forever, remember which is which? These are Greek terms. Scler means rigid, and rheo means something that is in flow, fluid, right? And that is the time dependency, right? Here the constraints are rigid in the sense not that they're not moving, but they're not time dependent. Here they're fluent with respect to time. This syllable rheo is another term that describes something that is very fluid. And the expression diarrhea has the same origin, same Greek origin. I promise you, you will never forget this. Sorry, I missed one. We have one last constraint classification, and that is between holonomic and non-holonomic constraints. Everything in our example are holonomic constraints. So to show you what a non-holonomic constraint is, I have to go to the next page. Non-holonomic constraints. If I think about explicit constraints, right, we kind of saw the sequence that if I have a relationship on a position level, I can get a relationship on velocity level, and I can get a relationship on acceleration level. Right? I can compute one from the other. And here I'm doing this for a scleronomic constraint. For a rheonomic constraint, we would have additional expressions. By the way, I will try to avoid talking about rheonomic constraints in this class and do everything with scleronomic constraints. At some points, I will say, okay, if you have rheonomic constraints, there's going to be an extra term. But it doesn't change the math down the road, because then just, that expression has this little partial FC partial t in there. So this way, going that way, works always. If you give me a constraint on position level, I can always derive the constraints on velocity and acceleration level. Why do I say that? Because going the other way, especially the step from velocity to position, does not work all the time. It only works for holonomic constraints. Mathematically, what this means is that the constraints on velocity level are not integratable. So we cannot integrate them to get constraints on position level. And this sounds very, very complicated. And in this class, sorry, it's not, because there's basically just one example of non-holonomic constraints that is relevant. And there, this idea becomes very clear that you cannot integrate them, because in these examples, we have more constraints on velocity level. So more constraints in velocity than in position. All right, more constraints. Yes?
Shouldn't be in x double dot an plus sign, not an equal sign?
Yes, this is all wrong. But this is one of the little tests, right, that I built into my script to see if the class is paying attention. Thank you. No, it's important that I correct these, because half of you have blindly copied, and then half a year from now you wonder. So I said there's only one example, has different names. Some call it ice skating, some call it the rolling coin. I'll call it skid steering. Question, what is skid steering? And this is video time. What you see here is called a bobcat. I think that's the brand name. There's the bobcat. The logo here actually says bobcat. Sorry, it actually says everywhere bobcat. Skid steering is the more general term. The way these guys work is they don't have traditional steering in the sense that you rotate your front wheels, but the axes are fixed. Instead, they have this differential steering where these wheels on the left and on the right-hand side can rotate independently from each other. And then if they rotate in the same direction, you go forward and backward. And if they rotate in opposite directions, you can basically turn on the spot. And this works for threaded vehicles, as you can see this here. And this works for wheeled vehicles. And then, of course, if you have some combination, you can go in circles of different diameters. This is totally silly. So this is an exposition of these vehicles. They have their sand pit, and they do this all day. So they drive around. He cleans up a little bit, and now comes in a different bobcat and starts digging again. It's grown-up people, both driving these vehicles and watching as they are playing.
Hot Wheels for adults.
Yeah, well, for nerds. I would say. You see a little bit the steering on the spot. Sorry, I have. There's one part that I want to show you because it's actually really fun. It's not part of the video. I don't. No, this is fun. So they can balance on their front wheels. And because of the differential drive, they can still steer. Right? So you don't need all four wheels. Here, yeah, wonderful differential drive. Sorry, I'm just showing this for fun. And now, okay. Do you want to see more? This is more entertaining than the dynamics class. Sorry. Skid steering. Here's my little bobcat. Top view. 2 wheels on each side. And I can do 2 things, right? I can have them run in the same direction, and this guy will drive forward or backwards. Or I can drive them in opposite directions, and I will turn on the spot. And then I can do any combinations to drive in smaller or larger circles. Now, there's one thing this guy explicitly cannot do. No, right? You cannot drive laterally. Does this mean you cannot get here? Would you buy a Bobcat if you could not get here? Probably not, right? So how could you get there? Maneuver a little bit, go back, and then maybe do this. Right? So what we see here, if I think about this in terms of velocities, I only have 2 degrees of freedom. If I think about this in terms of position, I have 3 degrees of freedom in terms of position. I can go to any location in this plane, but not immediately, right? Not instantaneously. Now, for a planning class, we would now talk about this for multiple weeks, because planning for non-holonomic systems is quite difficult. And the reason is because for non-holonomic systems, it matters what you do in which sequence. Right? In order to go from here to here, you have to make a plan that requires moving backwards and then moving forwards. If you would execute that plan in the reverse order, you would end up over here. Right? So the timing matters. What you do in what order matters. And of course, the same idea applies to cars in general, right? Where the kinematics are a little bit more complicated, but you sort of have to, for a car, it would be the same, right? You get out of this parking spot, you steer this way, you come back in. And that steering can be tricky because there's constraints, right? You cannot pick any steering angle, so you have constraints. And so planning for non-holonomic systems is incredibly difficult. Yeah. This is why parallel parking is so hard, because you have to deal with a kinematic system that has non-holonomic constraints. From a dynamics perspective, none of this matters to us, and we have, in a sense, the advantage that we don't have to worry about the plan. Either someone did the plan, and I know my positions, and I know my velocities, and I know my accelerations, and I'm doing inverse dynamics, and I want to compute forces, right? But the plan exists, someone made it. Or I do forward dynamics, where I know the torques, and there is no plan, right? I just know here's my sequence of torques, and I somehow have to generate motions. So I'm never bothered with this planning stage. We just have to worry about dynamics. And for dynamics, dealing with non-holonomic systems is actually quite simple. The solution to the problem that we have here, right? 2 degrees of freedom and velocity, 3 degrees of freedom and position, is simply to use different variables. To describe positions. Position should be red. And velocities. So far, I kind of implicitly assumed that I had position variables q And velocity variables, we called them q dot. And there was a fundamental relationship between the two, where it said the time derivative of q against time, this is what we call q dot. So in a sense, the same variable for positions and velocities. But even here, you could argue that there are different variables, because one is called q, the other is called q dot. And they're linked through this relationship where the time derivative of one is equal to the other. What we will do for non-holonomic constraints is that we use now different variables. So we use q for positions, and we give q dot a different name, and we call it u. And we now set the time derivative of q not equal to u, but we say this is some function of u. So dq dt is not equal to u, but is a function of u. What does this mean in our example? So let's draw our little bobcat. Sits here, position x and y, some orientation gamma. We called this x in the past. Here I will actually say this is q, because I don't have any constraints, right? I can go to any point in the plane. So my x variables and my q variables are exactly the same. So x equals q in this case, and so I will call this q. Position and orientation. In terms of velocities, I have a u1 that goes that way. And I maybe should do a directed arrow. So this is u1. Positive u1 brings me forward. And this is u2. Positive u2 will rotate. Right? So this here is equal to x. I just said that, so we have no constraint on position. How about velocities, right? So we say dq dt, the change of my q's is equal, right? Of course, we get x dot, y dot, gamma dot. How can I set that in relationship to u1 and u2? What is x dot relative to u1? Yes. So we have cosine of gamma times u1. In the y direction, same story, but now we get sine of gamma u1. And what is gamma dot? u2. Yeah. And this would be here our function f of u. So the time derivative of my position variables are a function of my velocity variables. And as I said, right, for us, this is never going to pose a problem because either we do inverse dynamics, then someone made a plan and will give us the x and the u. And the person who made the plan will have to make sure that the plan fulfills this equation. That's the tricky bit. Right? That's why non-holonomic planning is difficult. But from a dynamics perspective, if we get the plan, we get an x, we get a u, we can compute forces through inverse dynamics. If I do forward dynamics, I would get accelerations, u dot. I would integrate them to get u. I would run them through this equation to get x dot, or in this case, basically q dot, and then I would integrate q dot. Right? So from a dynamics perspective, again, it doesn't make difference for forward dynamics either, because I would get accelerations, I integrate them, and then in the integration, I just have to make sure that I not integrate u, but I take u through this function to get the time derivative of q, and then integrate that against time. So it doesn't make any difference from a dynamics perspective. If I screw this up and instead compute that integral over u1, what will that give me? That is the distance you traveled, right? So every car has actually an instrument to measure that, right? That's your odometer distance. Which is, I don't want to say this is not relevant information, what your odometer reads, but it has nothing to do with the motion of the vehicle. Right? You leave the house in the morning, car's in the garage, you drive the entire day, you come back, you get back into the house, car is still in the garage, actually again in the garage. Right? So it has not changed its position, q, but your odometer will read whatever distance you traveled. Right? You can also, if you're cautious about the resale value of your car, you can also do this the other way around, right? You say, I want to drive to work or to university in your case, but I don't want to run up my odometer. How would you have to do that?
Take the bus.
No, you want to drive. Yeah. Any ideas? This is borderline criminal, so. Drive backwards. So you would drive half the way to university, turn around through the non-holonomic maneuver, drive the rest of the distance backwards, and your odometer will read 0. Actually, I doubt that today's odometers will read 0, but sort of old cars. Does someone have an old car, right, where you have a mechanical odometer which really counts wheel rotations? And that does work, right? And you would get a distance traveled of 0, and you're here, which is kind of pointless, but helps with the resale value of your car. So this is the integral, and this is what I mean with you cannot integrate these constraints, because integrating the velocity in this case is completely meaningless. Similar. This holds for implicit constraints. Jg times x dot, Jg transpose times x dot equals 0 exists as a constraint, but we cannot integrate it, so there's no Gc of x equals 0. And in this example, to be honest, right, where q and x are basically the same thing, I would just have to rearrange these equations to get a implicit formulation of what we just saw. To wrap this up, right, there's no reason to be afraid of non-holonomic constraints. I know this because all of you have used non-holonomic constraints in this class, right? You didn't even realize it, and it didn't cause any major problems. And this is what we did in problem 8, where, for example, here in 8b, or in general, right, we represented orientations through a matrix, through 9 elements, and angular velocities by 3 vector. And when we integrated, we always had one of these relationships that somehow set these angular velocities in relation to, in this case, the coordinates the coordinates that you use to describe your rotation. So in 8b, right, alpha, beta, gamma are basically my position coordinates, and omega are my velocity coordinates. And those are clearly different. And when you integrate, right, in our integration step, we always had to run basically this line here to go from one representation to the other. But it didn't cause any larger problems. It was not the most efficient way to do the integration, of course, and that's why we came up with this other solution, where we're now using omega to represent velocities and a to represent orientations. But sort of this idea of using, of using different coordinates for velocities and positions is not something that's very difficult. Right? And you've all done it before. Good. Do you have any questions? Then I have 5 minutes, and I could start a new topic, and I don't. Let's end here. We have the exercise on Thursday. Don't forget the homework. Don't forget to bring your computer. Have a good week.